Figure 1324, polymorphism, virtual functions, and dynamic binding under the hood. In this diagram, we're going to help you understand how it is that polymorphism really works. So in the last program, we demonstrated for you the fact that we can use polymorphic processing via base class pointers or base class references that are pointing and referring to derived class objects. And to help emphasize the fact that we were really using polymorphism, we put those pointers and references as parameters to functions where there is no relationship between the original objects in memory and the function parameters as declared. So the compiler, when it's looking at those functions and compiling those functions, has no idea whatsoever what type of employee object it is going to receive as an argument. And yet, even in that case, we saw that the proper functions were getting called. So what we want to do here is take a look at a diagram that helps explain the process. Now, we're going to start in this leftmost column of the diagram. It turns out in most compilers, and this is not required, but this is a typical way that this stuff gets implemented. In most compilers, when you create a class that has virtual functions, the compiler automatically creates a so-called virtual function table, or what they call shorthand a V table, for that class. And basically what that table is just a bunch of function pointers that point to the individual virtual functions for that specific class and that class alone. Now, in the case of our employee class, our earnings function was pure virtual, which is basically an indication that there's no implementation of that function. And for that pointer, a 0 actually gets inserted in the employee class's virtual function table, indicating that that's a pure virtual function. Separately, the employee class's vtable has a print function that is specifically going to aim at the version that was defined in class employee. Now, as you move down the hierarchy, every class below employee in the hierarchy is now guaranteed to have virtual functions, earnings, and print. So every single one of the other vtables is going to have these functions, and it's conceivable that another class lower in the hierarchy could add another virtual function, in which case these tables could get longer, but for this example, all of the classes have the exact same virtual functions. So in the case of a salaried employee, the virtual function table contains two pointers, one that points to the earnings function specifically for salaried employee that returns the weekly salary, and one for the print function that's going to output the salaried employee's information. Similarly, for the hourly employee, we have a vtable that points to the earnings calculation for an hourly employee, and it points to the print function for an hourly employee that will output the employee's data. And also for the last two classes, the commission employee and the base plus commission employee as well. Now, in addition to these virtual function tables, every time you create an object using one of these classes, the compiler is actually going to add an additional piece of data to the beginning of the object in memory, and that additional piece of data is a pointer to the corresponding class's virtual function table. So when I created my salaried employee object for John Smith, that included the data for the first name, the last name, the social security number, and the weekly salary. But it also includes a hidden piece of data that you can't work with programmatically yourself, which is this pointer at the top of the object that's pointing to the beginning of the salaried employee's virtual function table. Similarly, when I create an hourly employee object, any object of a class that has virtual functions is going to have prepended to the object in memory a pointer to that class's virtual function table. So the hourly employee's first piece of data is a pointer to the vtable for the hourly employee, and then we have the rest of the hourly employee data. And similarly for the commission employee, it has a pointer to the commission employee vtable, and for the base plus commission employee, we have a pointer to the base plus commission employee's vtable. And the compiler's taking care of all of this for you. All these data structures and these extra pointers are being handled for you by the compiler at compile time. Now, you recall from our program that we created a vector of employee pointers with 4 elements in it. And in the first element of that vector, we placed the address of our salaried employee. In the second element, we had the address of our hourly employee. The third element had the address of the commission employee. And the fourth element had the address of the base plus commission employee. Now, what we want to look at is what happens when we use this pointer to invoke the print function of an hourly employee object. Now you'll recall that the first thing we did was to pass the address of that hourly employee to the virtual via pointer function. And when we passed that to the virtual via pointer function, it was stored in the variable base class PTR in the preceding example. So we take this employee pointer and we pass it into base class PTR. So now base class PTR contains a copy of this address, and of course, because it's a pointer, it's pointing to the object in memory. So that's what this dashed line is representing, the fact that we're passing the address into a function that is then storing that in its parameter base class pointer, and now base class pointer currently points to the hourly employee object. Now step 2 in this process is to get to the hourly employee object. When I say base class pointer arrow print, the arrow operator dereferences the pointer and moves me to the actual object, at which point I need to now call the function. Now the compiler knows that the print function is a virtual function. So and not only that, it knows that in the virtual function table for any type of employee object, that the print function has its pointer in the second element of the virtual function table. So what happens when I make that function call is first the dereferencing of the base class pointer to get to the employee object occurs, the hourly employee object. Then, because it's a virtual function call, we dereference the pointer at the beginning of the object to get to the virtual function table, and then based on which virtual function is getting called, it indexes into this virtual function table to the appropriate position where the pointer would be stored for that function print that is associated with class hourly employee. So you can see by the pointers here that it's not physically possible to get from the hourly employee object to the print function for salaried employee, the print function for commission employee, or the print function for base plus commission employee. Once we dereference that pointer, we are guaranteed to be looking at the appropriate employee object that needs to have a virtual function called, and once we dereference the initial pointer at the beginning of that object, we are looking specifically at the virtual function table for that class, and that virtual function table only refers to the virtual functions for class hourly employee, and therefore we are guaranteed that the appropriate print function is going to get called here. So as you can see, it's not really magic that's happening behind the scenes here, but rather a couple of pointer dereferencing and indexing operations that help us locate the exact right member function to call. And of course, when you call these member functions on any of the other objects, when you get from the base class pointer to the appropriate object and then dereference the initial vtable pointer, you will be looking at the appropriate virtual function table for that particular object.